All right, so today let's take a look at Newton's method. Newton's method is an algorithm. So it's an algorithm. So a series of steps, like actually laid out, which is nice, for finding zeros. Finding zeros. Is there any there? I don't know. Algorithm for finding zeros of continuous differentiable functions. Okay, that's what Newton's method is. It's a series of steps for finding the zeros of continuous differentiable functions. Okay, now particularly this is used for higher order polynomial functions. So like a linear function, easy to find the zeros, right? Quadratic functions, we've got the quadratic formula in order to derive those zeros. They're analogous functions for the cubic and the quartic, so the degree 3 and degree 4s. They're not quite as pretty as the quadratic equation, but they exist. There's closed formulas for the solutions of those zeros. But unfortunately, Évariste Galois proved that there are no such closed solutions for degree 5 or any degree higher. So in fact, there's no way, there's no closed formula for finding the zeros of any function of degree 5 or higher. Now, this will apply to any continuous differentiable functions. So there may be other types of functions where there isn't any clear method or straightforward way to find those zeros or solve for those zeros other than using some method like this to approximate them. Okay, so let's see. The idea of Newton's method, the sort of concept behind it, is so we've got some continuous differentiable function, right? We've got some function like this, say, and what we want to do is to find those zeros. How we'll start is we're going to pick a random point, pick any point close to a zero. Now, it can be a random guess, or we can maybe graph the function and get an idea of some point that's nearby. Okay, so let's say I'm looking to do, I don't know, I'm trying to find this zero here, say. So I pick some value that's close, like say here. Okay, and what we're going to do is we're going to take the tangent line and continue it down to the x-axis until it hits here. And now this, that new point there where that intersection happened, that's going to be my new x. Now from there, I'll take my tangent line till when it hits the x-axis. That's my new x, like there. And then I repeat and keep going. And what'll happen is you see that this tangent lines, these x's are getting closer and closer and closer to that zero. Okay, so that's sort of the idea behind it. But the cool thing is with Newton's method is once we have the formula, once we have the algorithm, all the geometry and algebra of finding the equation of the tangent line, projecting it down to the x-axis, finding its zeros, and all, that's all done for us. We don't have to keep redoing that. We just iterate through a process. But that's the conceptual idea behind it. Now, it does have some limitations, as we'll see once we lay out the formula, but one thing to note about it is that it will tend toward the closest zero. So in other words, if I pick this spot here and start doing my algorithm, it's going to tend toward that zero rather than this one or this one. So that if I want to get this one, I'm going to have to pick something maybe over here and start. Okay, so that's one limitation. It'll go to the nearest zero. The second limitation is like up here. those zeros aren't real. They're imaginary, right? We've got this dip, but it doesn't actually cross zero in the real world. Newton's method is not going to be able to find those, okay? So it's only going to be able to find these real zeros. And again, it will tend toward the nearest one. Now, the nice thing is that it will generally tend very quickly. That is, we don't have to do many steps most of the time in order to get a satisfactory answer, say, to however many decimal places we want. 9 decimal places or whatever it is. Usually the calculator, right? It's the 8 or 9 decimal places. So it's usually good enough. And this, in fact, is going to be the way, like if you plug in a 10th degree equation into the calculator, it spits you out an answer, no problem. But it doesn't have any kind of formula built in. It can't. So the question is, how does it do that? Well, this is one way to do that. Okay, now another thing to note, and we'll see it again when we get the formula out, it'll be a little more clear. But if I pick a starting spot like that, where my tangent is, or my derivative is 0, I'm going to have problems, okay? So this is another place, or this is a place where Newton's method can fail. If I get a derivative that's equal to 0, bad news. Other times it can just oscillate back and forth between two values and not actually approach a 0. These are the two ways that Newton's method can fail. Now, most of the time, the frequency with which this occurs is rare. It rarely happens that Newton's method fails, but when it does, usually the easiest solution is just to pick a different starting x. If we pick a different place to start, often we can skip past where it's getting hung up. Okay. So that's Newton's method and its limitations, sort of the idea behind it and what's going on. But let's get the actual algorithm here. Looks like this. X sub n plus 1 is equal to x sub n minus f at x sub n over the derivative of x at x sub n. Right. That's the key to Newton's method. This is the algorithm. This is what we use. Now, this is an iterative process. So iteration is different than recursion. It's recursion, that is, we're doing the same thing over and over again, but it's iteration in the sense that when we do our recursion, we're taking the output from the last time and using it as the input for the next time. That's iteration. Okay, so we need some place to start in general. We'll say x sub 0 is some guess. It's some random number. It can be any number, just pick one. But we usually try to get one that's relatively near to our 0 for the reasons that it's going to approach the nearest 0, and the closer we are to the actual 0, the less steps it's going to generally take. Okay, so we pick a guess near our 0. Now, how do we know what's near? Well, just graph the function or something, or it can just be a blind guess. Okay, and then x sub 1, the next one, we're going to take our previous answer, x sub 0, or our previous guess, subtract our function at that place, divided by the derivative at that place. So we've got this x0 from our initial guess, and then we're going to get the next x by iterating through and plugging in those that first x value to get the next one. And then likewise, x sub 2 is going to be x sub 1 minus the function evaluated there divided by the derivative there. And so on, right? Until we get our desired accuracy, 3 decimal places or 4 or whatever it might be. Okay, nice. Now, now that we've seen the actual function, it's clear to see that if our derivative is 0, then we're in trouble, right? If our derivative is 0 at x sub n for some n, then we've got to divide by 0 and things are blowing up and we've got problems. So like I said before, usually the easiest way to fix that problem is just pick a different starting guess and run with it. Okay, cool. So let's try a couple examples here quick. Let's say 2 iterations of x squared minus 5 with x0 equal to 2. So this is our f. Okay, so nice. We don't actually have to guess or do anything for our x0. They gave it to us to start. So we got x0 is 2. Cool. So now I'm on the path to finding the next x. So again, our algorithm is xn plus 1 is xn minus f at xn over the derivative at xn. Okay, so x sub 1, I'm going to take my x sub n, which is 2, the one before x sub 0, 2, minus, now I need to evaluate my function at that x, so 2 squared minus 5 is a negative 1. And let's see, what's my derivative here? Derivative of f is 2x, derivative of a constant is 0. So my derivative there at 2 is 4. So it looks like 2 plus a quarter. Oops. 2 plus a quarter. That'd be 8 quarters, so 9 quarters. All right, so that's my next x. Second iteration. I'm going to take my previous answer, x sub 1. That's my x sub n, so 9 quarters. Minus, I need to evaluate my function at that, so that would be 9 quarters square minus 5, divide by, and I need to evaluate my derivative there, 2 times 9 quarters. Okay, that's 9 quarters minus 81/16 minus 5 over, this would be 9 over 2. Let's see, 80/16, so that's minus 1/16 over 9 halves, 9 quarters. Sorry, I'm just doing some algebra here now. Hopefully I did that right. 50 and 30, so 80, 1/16. Reciprocal, 8 times 9 is 72. 9 quarters minus 1 over 72. And whatever 9 quarters minus 9 over 72 is, let's cheat. 9 quarters minus 9, 1 over 72. Math to frac, 161 over 72. There we go. And so there's our x2. And then for x3, we keep going round and round. But we're just challenged to do 2 iterations for this one. Nice. So that's it. It ends up being quite a bit of algebra work. But the cool thing is, like I said, generally it'll approach your actual 0 relatively quickly. So you can get the accuracy that you want pretty fast. let's, I don't know, how about square root 2? Square root 2 is a pretty important number, so let's estimate square root of 2 to, I don't want to make too much work for us, but it might come really quick. Let's try 4 decimal places. Okay, so estimate root 2 to 4 decimal places. And you might think, well, how am I going to estimate a value of a number? Well, we were just talking about the zeros of a function, weren't we? Well, think about it. This is one of the solutions to x squared minus 2 equal to 0, right? This x is equal to plus or minus root 2. So one of our zeros is this square root 2. All right? So estimating the root 2 is the same thing as finding the 0 of this function, x squared minus 2. Cool. All right, well, let's see. Root 2, let's use the calculator to get an idea of what it is. Root 2 is approximately, according to the calculator, 1.414213,562 is as accurate as that gives us. Okay, 414,213,562. All right, and we wanted at least 4 decimal places, 1, 2, 3, 4, so we want to get to there. That might be, we might get that real fast, but we'll see. All right, so let's pick a number that's close to that. Let's say 2. Okay, so x sub 1 is going to be x sub 0, which is 2, minus my function value. Oh, this is where it's going to freeze, eh? What's my derivative? Oh, derivative of x is 2x, and yep, 4. So we get 2 again, and round in circles, we just froze there. Okay, so let's pick a different starting value. Let's try let's try 1.5. It's a little bit closer even. Okay, so then x sub 1 is going to be 1.5 minus, I need to evaluate my function at 1.5. So 1.5 squared minus 2 is a quarter. Let's see. I'll just leave it in decimals for now, because we're going to estimate in decimals. So we got 1.5 squared minus 2, that's 0.25. And I need to evaluate my derivative there. So 2 times 1.5 is 3. And let's see what we get there. So we've got 0.25 divided by 3, and 1.5 minus that. Math to frac. Oh, well, I don't need to math to frac it. We've got 1.4166666667. Something like this. Okay, so in our first iteration, it looks like we got 1 and 2 decimals already, but we're wrong here. Okay. So now this is our new x. So x2 is 1.41666666. 6 is all the way down, right? That last 7 is a round up because of the calculator. Minus, now I need to evaluate the function there. So let's take squared minus 2 which is 0.00694444. Okay, and I need to evaluate my derivative there. Multiply that by 2. So 1.416666 times 2. We got 2.8333333. There's a 2 there, but okay. All right, and now let's see what that is. 1.41666666 minus 0.0069444444, however many, divide by 2.8333333. We've got 1.41421566. Oh, we got an extra decimal already. Nice. So we got 1, 4, 1, 4, 2, 1, and then we're wrong in that decimal place. One more, you see that these numbers are getting super, super tiny, right? This number here, the correction off of this is, it's even divided. It was already a 0.00, and then we're dividing it even further. So these changes are getting smaller and smaller and smaller as we go along, and so we're just looking for our decimals to match to whatever accuracy we want, and then we can stop. Once they start repeating, and we see no change, then we can say, okay, that's it. The changes are all smaller than that forevermore, so we can stop. Nice. All right, that's Newton's method.